So next we want to introduce some notation. I guess you call it exponent notation or exponential notation. So if I have a positive integer m and I write a to the m power, so a here is an element of the group, let's say. M is a positive integer. So a to the m power literally means I take a and start together a bunch of times. And in fact, we have m copies of a. M copies of a. If I were to write a to the minus m, that notation means I'm taking a inverse and starring together a inverse multiple times. So a inverse, we have m copies. If I were to write a to the 0 exponent, that notation is conventional for just the identity element. Now basically, we're defining these things to be this way. So we want to be able to distinguish between the different types of notation. And so sometimes, if you're dealing with, let's say, if my star operation is addition, some type of addition, could maybe be matrix addition or just ordinary addition for integers or addition for, I don't know, Zn. Then if I were to write a to the m power, this would actually be a plus a so on plus a, and you'd have m summands. So I know that can be confusing because we're used to seeing a to the m power. A to the m power means multiplication, but when the operation is addition, it just means you're repeating a over and over again with the operation being addition. Most of the time, though, in your book, so alternately, if I can spell alternately, if the star operation is addition, oftentimes you'll see this notation, you'll see MA instead. That's a better notation in my opinion, MA, because what does that mean? That just means you're taking M copies of A. So you have A added together a bunch of times. M summands. So just be aware that you could see either notation. Either notation. So this is the non-confusing one, right? This is not confusing. And this one can be a little confusing though. The green one is a little confusing. But just be aware, sometimes you'll see a to the m and it actually means adding a together. Now, if your star operation is a form of multiplication, then there's no ambiguity about what a to the m means, right? It just means you're actually multiplying a together a bunch of times. So these would be m factors of a. So no ambiguity there. Another type of operation we've seen, the star operation, could be functional composition. So that applies to, what does functional composition happens? That happens when you're dealing with permutations, right? Permutations on a set, or you actually can compose like reflections and symmetries on an n-gon. So elements of dihedral groups. So in that case, if you were to write, I don't know, for example, like sigma to the m power. So let's say sigma is a permutation. That would mean sigma composed with sigma, composed with sigma. Now just say you have m copies in this case. M copies of that permutation. So you're composing that permutation over and over and over again. Yeah. So what else do I want to say here? I guess we want to do a theorem. Theorem 7.7. So this basically is your properties of your exponents. So you could do this for multiplication, you could do this for addition, you could do this for functional composition. We're going to do it more generically for star operations, though. So it applies to all of those when you have a star operation. Let G be a group. And let A be an element of G. Then number 1, a to the m power starred with a to the n power equals a to the m plus n power. This is for all m and n integers, for any integer. It doesn't have to just be positive integers, it could also be negative integers. 2, so I'll say and 2. A to the m power raised to the n power is a to the m times n. This is for all m and n integers. So I don't know if I'm going to do the negative cases. I think I might just do the positive cases. You can do it for the negatives. They're not super hard. You just have to do a little, I guess, bootstrapping. But let's see, proof. Let G be a group. And let A be an element of G. We're going to start with 1. So first, maybe I'll do both. Maybe I'll do positive and negative. Consider the case when, so let's just let m and n be positive integers. Okay. Then if I look at a to the m starred with a to the n, this would be a star dot 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 star a, m copies, right? And then we're going to star that with what? A star A, n copies. So if you count up the total number of copies of A you have, you're going to have m plus n copies, right? A star A. This is m plus n copies. In other words, this is simply a to the m plus n power. I'll do the negative case. So we're assuming m and n are positives. I'll do a negative now. So I'll do also, let's look at a to the minus m star, a to the minus n. Now what does this mean? This means a to the negative 1 star, a to the negative 1 star, a to the negative 1. This is m copies. Then we're going to star that with a to the negative 1, star a to the negative 1, star a to the negative 1. This is n copies. Now you put that together, well, don't want to do that. You have A inverse, star A inverse, star A inverse, m plus n copies, right? You have m copies here, n copies there, that's m plus n copies. And this would simply be a to the minus n plus n. Yep, that's exactly the theorem. Okay, so what else do we want to do? I guess technically you got to do like 0 cases. I'm not going to bother with the 0 cases. the cases when you're dealing with 0. I mean, you can. It's got so many subcases. Okay, I want to do 2. So that's kind of like a partial proof. It doesn't go through all the subcases, but I don't want to do that. What if we have a to the m to the n? So let's note a to the m to the n. So first I'm going to do in parentheses. Whoa, what happened here? In parentheses, let's make this red in parentheses. This is for positive m and n. You have a star, dot, 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 star a. There's m copies. This is raised to the n power. So what does that mean? That means we're going to have a star, dot, 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 star a. M copies of that. A star, A star, A star, A. M copies of that. And we're going to keep doing that. A star, A star, A. Oops, I don't need another one. Let's put some dot, dot, dots. A. M copies of that. And how many of these M copies are there going to be? There are going to be N copies of these M copies. So if I have N groups of M's, that means I'm going to have M times N copies altogether. So there's going to be A star, dot, 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 star A, Mn copies. Okay. What else do I want to say here? What about the negative cases? Okay, we'll look at negative m and negative n. Let's do that. I don't really like the negative cases. If I write I never finished it. This is what? A to the m times n. Okay, my bad. I never finished it. Okay, let's look at a to the minus m. Whoa, what happened to my... disappeared. There it goes. Minus m to the minus n. So what does this mean exactly? Yeah, it's a little tricky. A little tricky. So first I'm going to start with the a to the minus m. That means I have a inverse starred. A inverse starred. A inverse. Right, and that's to the... there are m copies of that. So now all of that's raised to the minus n power. The minus n power. So what does exactly that do? I have to make some space here. This is going to be what? A inverse starred. A inverse starred. A inverse. And because we have a minus here, that means we're going to take the inverse of this. And we're going to do that n times. N times. So that's my first time. I'm going to have A inverse star. A inverse star. Oops. Dot, dot, dot. Oops. There it goes. A inverse. And then we're going to put a little minus 1 there. That's the second time. And then we're going to do this a bunch more times. And then we're going to do A inverse. A inverse, this will be the last time. A inverse, and this is going to be the last time. This is going to be the nth time we do it. We put a little negative 1 there. So there are n copies of this garbage. Oh, I forgot to label each of these. There are m copies of this, m copies of this, m copies of this. Okay, so now what we're going to do, we're going to take that negative 1 and we're going to basically use our corollary 7.6 here. Corollary 7.6 with this, the blue negative 1. So corollary 7.6 applies here, and what it does, let me show you how this works. Okay, so this a to the negative 1, that was the last element in that first parentheses with the red, with the blue negative 1 there. So we're going to take a to the negative 1, blue inverse, starred, dot, 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 and we continue, then we're going to go on. A to the negative 1, and that's going to get blue inversed, starred, and then we're going to go here. A to the negative 1, right? We have to do it in reverse order. That's what theorem, or what was it? Corollary 7.6 said. You do your inverse when you're doing the star in reverse order. Remember what that was. Where was it? Right, if I have A, B inverse, I have to do B inverse, A inverse, right, in reverse order. That's what I'm doing right now. I'm doing these in reverse order. So this gets an inverse. Well, that's the first one. There are going to be m copies of this. So you'll notice the same thing happens. And then a little star in there. A little star in there, a little star in there. This happens to everything. I'll just say, okay, you get A inverse, inverse, star. A inverse, inverse, star. A inverse, inverse. Oops. I don't need that one. I can just do a dot, dot, dot there. Come on. Right. That's the second one. There are m copies here. You got dot, dot, dot. And you go all the way to the last one. You get A inverse, inverse, star. A inverse, inverse, star. A inverse, inverse. There are m copies here. Remember, there are a total of n copies of all of these. N copies of m. Now let's simplify. Remember that A inverse inverse just gives you A. So you're going to have what? A star, dot, 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 A star, dot, 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 A star. Should have been a star here. Star here. You're going to have a bunch of A star, A star, dot, 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 A star, dot, 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 A star, A star, dot, 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 A. So m copies, m copies, m copies. A total of n copies of these m copies. N copies of m copies. Well, that's just the same thing as A star, A star, A a bunch of times, m times n copies. But what's that? That's what? A to the mn, or you could say A to the minus n times minus n, right? Because mn is the same thing as negative m, negative n. And that proves it, right? You can just multiply negative m and negative n together. Okay, that's good enough for me. I'm not going to do the zero cases where you have zero exponents. I'm just doing positives together and negatives together. All right, so that proves that. A little tedious. I'll stop there.